Swayam Prabha. Digital India. Educated India.
In the previous lecture, we discussed about the response analysis of structures subjected to multi-point excitation, and how we obtained the power spectral density function matrix for the responses given the power spectral density function of the ground excitation. And this power spectral density function of ground excitation was converted to a power spectral density function matrix of the excitations at different supports with the help of the influence coefficient matrix R and the various vectors or the vectors of excitation at different supports that led to a matrix called Sx double dot G matrix, which denotes the power spectral density function matrix of the excitations at different supports, in which the diagonal terms are the power spectral density of the excitations at different supports, and the cross power spectral density terms represent the cross power spectral density between different excitations at different supports, and that is we are representing with the help of the matrix Sx double dot G. That is a matrix, and it has cross power spectral density terms. Once we have these matrix defined and the R the influence coefficient matrix that is known, then one can get the power spectral density function matrix of the displacements or responses Sxx. This will not be Sx double dot G, this will be Sx. So, Sxx as H m R Sx double dot G, then the transpose of these quantities H m R on this side, that is RT MT, and H becomes now a complex conjugated transpose of that. So, that is a formulation that we have proved before, and if we were wanting to obtain the cross power spectral density function between the excitation and the response displacement, that is Sx double dot G x, that is equal to minus H m R x double dot G, where x double dot G is a matrix of size S by S, where S is the number of supports and R of course is a coefficient matrix of the size n into S. Also, we discussed in the previous lecture that many a time we are not interested in obtaining all the responses, but we may be interested in only a selected few. In that case, a reduced frequency response function matrix is obtained from the total frequency response matrix of the system, and that we denote by H bar, and using that H bar one can obtain the power spectral density function of the selected or matrix of the selected responses. Then we as an example, we solved a problem in which we had 3 supports and 2 non-support degrees of freedom, U1 and U2, and we discussed how we obtained the cross power spectral density function terms of the power spectral density function matrix of the excitation. With the help of that, we obtained the values of the power spectral density function or the power spectral density function of the response U1 and U2, and from that the area under the curve provided us the root mean square value of the responses, and these root mean square values of the responses were compared with the time domain analysis. Note that the excitations were the El Centro earthquake record and the El Centro earthquake power spectral density function. They are the inputs respectively for the 2 kinds of analysis. So, you can see that comparison was very good. We now solve another problem in this class, the problem of the pitch roof portal frame, in which we had 2 degrees of freedom, if you recall, one at the as the sway degree of freedom on the left hand side, and the other one is a vertical degree of freedom at the crown. So, this is the problem that we had solved before for the ground excitations, which had a time lag of 5 seconds, and for that we derived the R matrix, and this was the R matrix, and also we derived the mass matrix. If you recall, the mass matrix for such systems is not a diagonal mass matrix, but they are the coupled mass matrix, although we are using the lumped masses at the different degrees of freedom. So, the derivation of this also was worked out before. This is the K matrix. So, with the help of the K matrix and the M matrix, the frequencies, 2 frequencies of the system were obtained. They are 5.58 and 8.91 radian per second, and with the help of these 2 frequencies we obtained the values of alpha and beta to construct the C matrix, and the C matrix thus was obtained. Then for obtaining the value of the C matrix, after we have obtained the value of the C matrix, then we use the usual formulation, that is the equation that I had shown before. So, we plugged into this equation, and in constructing H matrix we have K minus M omega square plus I C omega, inverse of that becomes the H matrix. So, once we know this H matrix, then we obtain the values of Sxx, and the Sx double dot G matrix was obtained in this particular fashion, and the cross terms were one cross term was exponential of minus 5 omega by 2 pi, because between the 2 supports, the first support and second support, there was a time lag of 5 seconds, and the first support and the third support, the time lag was 10 seconds. So, therefore, they appear like this, 1 row 1 and row 2 into this matrix, and the results were compared, and for the 2 cases, that is, in one case we had a perfectly correlated excitation, that is at the 2 supports the excitations were same, and in another case we obtained the excitation having a time lag of 5 seconds. Next we discussed about the power spectral density function of absolute displacements, and in order to obtain these power spectral density function of the absolute displacement, what we have to do is that we have to add to the relative displacement x to the displacement or quasi-static displacement that is introduced at the degrees of freedom because of the ground displacements at different supports. So, in order to get that, we multiply the xg vector, that is the excitation vector at the different supports, with the R matrix, and that gives us the contribution of the different displacements of the excitations to the non-support degrees of freedom, and the relative displacement was x, that is the with respect to the base, the displacement of the different non-support degrees of freedom, and that is multiplied by or pre-multiplied by a identity matrix I. So, this becomes the addition of these two becomes the absolute value or the total value of the displacement at different degrees of freedom. And once this relationship is obtained, then using this relationship one can write down the value of the power spectral density function matrix like this, that is Sxx is for this term, because I Sxx it will be Sxx itself, then R Sx g RT, where Sx g is the power spectral density function matrix of the ground displacement, and then I Sx xg and Sx g and x. So, they are the cross power spectral density function matrix between the displacement and the ground excitation or ground displacement, and this is the other part of the cross power spectral density function matrix, which generally is a complex conjugate of this and transpose that you have seen before. So, once we have this expression, in this expression this is known, this we have already obtained, this is also given, because if the power spectral density function matrix of the ground acceleration is given to us, then from that one can construct the power spectral density function matrix of the ground displacement. And in order to get the value of Sxg and Xgx, we use this equations, that is first we obtain the value of the cross power spectral density function between the excitation and the displacement using this standard expression, in which it is Sx double dot g and Xs double dot g is replaced with the help of the Sxg by multiplying it with the help of omega square. So, this and the complex conjugate of this Sxg is a complex conjugate of Sxgx. If this matrix is a complex matrix, then there will be a star over here, star and a transpose, and if it is a real quantity, then the star does not come into picture, it is simply a transpose of that. Now, with the help of this, we wanted to obtain the response of the pitch roof portal frame, and for that we are interested in finding out the response of the system, not only for the not for the relative displacement, but for the total displacement. So, the for obtaining the total displacement, we have to know the first Sx Gx Sx matrix. So, that is given in this particular form, and since Sxg and Sx double dot g, they are related by a relationship that Sx double dot g is equal to omega to the power 4 into Sx double dot g that we have seen before. Then if we substitute that relationship over here, then this becomes h m r omega minus to the power 2 into Sx double dot g, not Sxg, and this Sx double dot g is known to us. And Sx double dot g can be constructed from the time lag that is given to us, that is a 5-second in the time lag. So, this Sx double dot g matrix would be equal to this C11 multiplied by Sx double dot g. Mind you, this Sx double dot g is a single quantity, that is the power spectral density function of the earthquake, that is the L center earthquake that we have considered, and this when it gets multiplied by C11, then it gives the power spectral density function matrix between at point 1 and at 4.2 the excitation becomes CT2 and into X double dot G, and obviously this C11 and C22, these values are equal to unity, and C12 and C21, they are the cross power spectral density function terms, and we had seen before that for the same earthquake producing different kinds of excitations at different supports, they are the cross power spectral density function between the excitations is equal to the power spectral density function of the earthquake, that is a single quantity, multiplied by the coherence function Cij, and coherence function is given or defined in this particular fashion, and we use some empirical relationship for obtaining the C12 or C21, etc. Sx Gx matrix will look like this, that is the cross power spectral density function matrix between the ground displacement and the non-support degrees of freedom displacement x will be like this, that is Sx G1, that is for the first support, and this is x4 is the displacement, sway displacement of the pitch roof portal frame. So, Sx G1 Sx4 represents the cross power spectral density function between the excitation 1 support to the displacement x4. Similarly, Xg1 Xg5, that indicates the cross power spectral density function between the excitation at support 1 with the displacement x5. And in that fashion, one can also describe the cross power spectral density function between the support 2 and the displacements 4 and 5. So, that gives us the XGX matrix. However, this XGX matrix can be computed easily with the help of the above relationship, that is the relationship that we have used, and once we take that relationship, then what first we have to obtain is the power spectral density function matrix of excitation. Sx double dot G is the L center power spectral density function, and the C11, C22, C12 terms, this will be 1 1 obviously, and this will be the rho, and rho will be equal to exponential of minus 5 omega by 2 pi is equal to rho. So, one can work out this value of C12 for every value of omega, and so this matrix is completely defined. And then we write down the cross power spectral density function matrix between the ground excitations and the displacement x, and that is written as H m r x Sx double dot G divided by omega square. That becomes the relationship for Sx double dot G, and this because Sx double dot G over here is equal to omega to the power 4 into Sx G. So, using that relationship we get omega square below over here. That is how the omega square at the denominator has come. Then HMR divided by omega square, this we take out, and then Sx double dot G matrix, that is written over here. The H matrix is nothing but K minus M omega square plus IC omega inverse of this. So, you substitute for H, then this gets multiplied by M, and then multiplied by R, and then this matrix, and this is a single quantity Sx double dot G, that is the power spectral density function of the earthquake, that is the L center earthquake. And all of them are 2 by 2 matrix. Therefore, this multiplication of the matrices for a particular value of omega leads to a 2 by 2 matrix of this form, AI omega into Sx double dot G. Since there is a this term will be a complex term, so this matrix is expected to be a complex matrix of size 2 by 2, and that multiplied by Sx double dot G. And once we know the value of this matrix Sx Gx, then one can obtain the S x x g as the this is S x x g is equal to S star t x double dot G. See that here, since it is a complex matrix, we take a complex conjugate of that and then transpose in order to get Sx xg from xgxx. So, once these two quantities are known to us, or these two matrices are known to us, one can substitute them into this particular equation, equation 4.81, and in equation 4.81 we know Sxx, then Rx G, that is also Sxg is known. So, this R is also known. So, therefore, this particular term is also known, and we have obtained Sxxg and Xgxj, and therefore, all the terms in this equation are known. So, one can get the power spectral density function matrix of the absolute displacement of the pitch roof portal frame for degrees of freedom 4 and 5. 4 is the sway degree of freedom and 5 is the degree of vertical degree of freedom at the crown. So, that is how these power spectral density function of the degree of freedom 4 and degree of freedom 5, A represents the absolute value. So, the power spectral density functions of these two quantities are obtained and plotted against frequency, that is for degree of freedom 4, and this is for degree of freedom 5, and one can see that the for degree of freedom 4 the value is more compared to the value of the power spectral density function of the degree of freedom 5, because this is of the order of 10 to the power minus 5, the other one is of the order of 10 to the power minus 3. And the area under the curve of course provides us the root mean square value of the absolute displacement of the degree of freedom 4 and degree of freedom 5. So that is how one can obtain the power spectral density functions of the absolute displacements if it is required. Next we come to the power spectral density function of the member forces. Once we obtain the power spectral density function of the displacement, that is the displacement of the various translational degrees of freedom, then from that one has to obtain the power spectral density function of the membrane forces. And for that we take say this particular frame, and here say this is the frame. In this frame we have say 1, 2, 3, 4 supports, and at these 4 supports we have got 4 different excitations because of the time lag between them, and these are the non-support degrees of freedom, that is x1 to x6, they are non-support degrees of freedom. And say we are interested in finding out the power spectral density function of the bending moment at I and j. So that is of our interest. So then what we do in the beginning, that we write down the matrix, the stiffness matrix of the entire structure with these rotations, and once we know the rotations, then from there one can get the relationship between the rotation and the displacement, and this matrix is called a matrix A. Say once we know the relationship between the theta matrix, theta vector and the x vector through matrix A, then one can obtain the power spectral density function of the rotations in terms of the power spectral density function of the displacements using this equation. And the cross power spectral density function between the displacement and the rotation is given by this AX, and the S theta x will be simply the transpose of this. Now, if x theta x is a complex matrix, then of course there will be this will be a complex conjugate and then transpose. Now, once we have obtained these S theta theta, that is the power spectral density function matrix of rotation, and the power spectral density function matrix of displacement, and the cross power spectral density function matrix between rotation and displacements. Once they are known, then from that from those matrices one can select the specific terms of the power spectral density function to construct the power spectral density function matrix, which will be used in finding out the power spectral density function of member end forces. Now, for example, if I take this column ij that I had shown in the figure, then the values which are required to find out the bending moment at the ends I and j are xi, theta I, xj and theta j. So, these are the particular displacements and rotations which are required. So, we take out that and we write down the relationship between the member end forces and the member end displacement with the help of the usual equation F is equal to k into delta. And once we are able to write that, then SFF, that is the power spectral density function matrix of the member end forces, becomes equal to k into S delta delta kt. This k is known, that is the member stiffness matrix, and S delta delta is the, or delta delta, they are the member end displacement. So, by knowing S delta delta, one can easily find the power spectral density function of the member end forces. In many cases, we want the member end forces in the local coordinate, that is the member end coordinates. Then of course, there a further transformation is required. That means, if the delta bar is the displacements in the local coordinate, and if delta are the displacement in the global coordinate, they are related through this relationship, that is delta bar is equal to T into delta, where T is the transformation matrix, and substituting for the delta bar, that is one can obtain the power spectral density function matrix of the member end forces in local coordinate to be equal to k into S delta bar, and S delta bar is further converted to S delta delta by including the transformation matrix T. So, it is possible to obtain the power spectral density function of the member end forces both in the global and the local coordinates, that is their power spectral density function of individual quantities, maybe bending moment, shear force, etc. Now, in this example, the displacements 1 and 2, that is the, if you recall, that is the example problem for the yes, I think, yeah, this is the problem. If we recall, we had solved for the for finding out the responses in time domain, where we specified the ground motions at these three supports, and they were the same ground motion, and this was a model of a pipeline, buried pipeline, and these supports, there were three supports were taken, the soil damping and stiffness matrix, or the damping and the stiffness are replaced by spring and dashpots, and these values were given to us, and the degrees of freedoms were 1, 2, 3, they are the translational degrees of freedom, and a rotation here. So, one can easily condense out this rotational degree of freedom, and once you condense out this rotational degree of freedom, then with the help of the translational or matrix, stiffness matrix corresponding to translation degrees of freedom 1, 2, 3, one can obtain the responses for the degree of freedom 1, 2, 3. Now, the stiffness matrix for the system was this 3 by 3 stiffness matrix. We obtained the damping matrix using C bar is equal to alpha m plus beta k, and the three frequencies that are obtained from this K matrix and M matrix. So, that were 8, 9.8 and 12 radian per second, and then we obtained the displacement power spectral density function for the 3 displacement, and using the same procedure that we have discussed before, but now we are interested in finding out the power spectral density function of the bending moment at the center. Now, for that we recognize the fact that at the center, if all the 3 degrees of at all the 3 supports, the ground excitations are the same, then we expect that there should not be any rotation over here, and in fact it can be easily shown with the help of the condensation matrix. So, if there is no rotation, then S theta theta will be 0 and Sx theta also will be equal to 0. That is the power spectral density function of the rotation and the cross power spectral density function of the rotation and displacement, they will be equal to 0. Now, if we wish to find out, say, bending moment here, then the displacement that we should take, this will be the displacement 1, and then if there is a rotation over here, say theta 1, this is a theta 1, and then the displacement here x2, and then the rotation here theta 2. So, if we know them, then with the help of that one can obtain the power spectral density function matrix of the bending moment at this point and in this point. Now, since at this point the bending moment is equal to 0, so we need not include this theta 1 into this vector, and we can modify our stiffness coefficient for bending moment for this member accordingly, so that this theta 1 need not be considered, and since theta 2 is 0, then we get only x1 and x2. These are the 2 displacements. If we know these 2 displacements only, one can find out the bending moment at this point, and that bending moment can be written by simply by this equation 3 ei by L square into x2 minus x1 in the matrix form. This becomes minus 3 ei by L square, 3 ei by L square into x1 and x2, where x1 and x2 are the displacements at these 2 points. And this can be further written in this particular form, that is the S bending moment, that is the power spectral density function of the bending moment is equal to k Sxx kt. So, if we know Sxx, one can find out the bending moment at this particular point. Now, the important part of this analysis is that if the ground motions are not the same at different points, then the relative displacements at this point and in this point, and from that one cannot obtain the bending moment at this particular point, that is at the center, that the way that we have obtained the bending moment. In that case, what we have to do, we have to find out the absolute displacement or the absolute displacement power spectral density function of 0.2 and the power spectral density function of the absolute displacement at 1, that must be known, and the cross power spectral density function must be known. Or in other words, we must have a power spectral density function matrix of the absolute displacements at 1, 2, 3 degrees of freedom. And for this particular problem, we need not bother about the rotation here, because the rotation becomes 0 if the degrees of freedom are or the excitations are same at these 3 points. But if they are not same and we are wanting to find out the bending moment at this particular point, then we wish to have the power spectral density function matrix of the absolute displacements at 1, 2, 3 and a power spectral density function of the rotation. However, the power spectral density function of the rotation at this point will not be affected by the ground displacements that is taking place at this point at different points with different displacements will not be affected by that. This theta can be obtained, S theta theta can be obtained from the relative displacement itself. So, therefore, what we do is that in obtaining the cross power spectral density function matrix of these absolute displacements, we go back to the previous problem that we have solved, in which we should know the power spectral density function and matrix of the relative displacement, then power spectral density function matrix of the ground displacement, then Sxxg and Xgxx that we had solved in the previous problem, and with the help of that we obtained the power spectral density function matrix of the absolute displacements, and then we obtain the bending moment, that is S bending moment here in place of Sxx. Here this Sxx is the power spectral density function matrix of the relative displacement, that would be replaced by the power spectral density function of the absolute displacements. So, the problem in which we have got the same excitations at different supports, we do not have to find out this absolute displacement power spectral density function matrix. We can only obtain the power spectral density function matrix of the relative displacement. However, the problem becomes slightly complex if we have a power spectral density or the ground excitations at different supports are different, and for that remember that one has to find out the power spectral density function matrix of the absolute displacements or total displacements of different degrees of freedom, and also we have to find out the condensed out the power spectral density function matrix of the condensed out degrees of freedom, that is like rotations theta theta etc. Theta theta, and the cross power spectral density function between theta and x. So, all those things must be known, then only one can obtain the power spectral density function matrix of the member end forces. Thus, we see that to find out the power spectral density of function of the member forces for excitations which are same at different supports, the formulation is simpler. But if you are wanting to find out the power spectral density function of member end forces for a multi support excitation problem, then one has to obtain the power spectral density function on matrix of the total displacement, and then from there we have to take out the relevant terms to form the power spectral density function matrix S delta delta, and which can be multiplied with the stiffness matrix K and Kt to obtain the power spectral density function of the membrane forces. So, these problems, the power spectral density function of the absolute displacements were and the bending moment were plotted in these figures, and the displacements and RMS values of the displacement and bending moments were obtained for different quantities. Next we come to what is called the modal spectral analysis. Now, since we use the mode superposition technique to uncouple the different equations of motion of a multi-degree freedom system, and can simplify the problem, that is a multi-degree freedom problem can be converted to a set of single degree freedom problems, and for each single degree freedom problem one can obtain the responses in the generalized coordinate, and from there one can obtain the displacement in the structural coordinate using the mode shapes. So, extending that concept, one can develop also a modal spectral analysis. The name modal spectral analysis comes because we are using the mode shapes of the structures for developing this method, and that is why it is known as the modal spectral analysis, and it has the same advantages that we observed for the case of usual time domain analysis and the frequency domain analysis. So, for multi support excitation we have this standard expression that we have discussed in connection with the mode superposition technique. So, the ith generalized displacement, velocity and accelerations are z dot I and z double dot I, and m bar I is the ith generalized mass, and JIT is the transpose of the first mode shape, R is the influence coefficient matrix associated with x double dot g, considering x double dot g to be a multi support excitation. Then one can convert this to this form by dividing by m bar I, and this entire thing is called Pi, that is the generalized force at the for the ith mode. So, or in other words, this is the ith modal equation, and in that m bar I is defined in this particular way, that is already known to you. Now, once we have a single degree freedom equation for a mode I, then one can write down z I omega to be is equal to h I omega into p I omega, and once we have this, then we can easily find out S z I very easily, that is the power spectral density function of the generalized displacement z, that will be is equal to h I absolute square multiplied by S p I omega, and one has to simply find out what is the S p I omega. Okay. Now, this S p I omega, since it has a relationship like this, then one can obtained using the formulation that is a y vector, or y is equal to a multiplied by x vector x double dot g. For that, using that relationship, we can find out Sy, that is the Sp over here, that is the power spectral density function of the force Sp, that will be equal to A into Sx double dot g into At, where A will be equal to this entire this JIT m r divided by m bar, that will be the matrix A. So, that one can easily obtain the value of Sp, and once we obtain the value of Sp, then one can get the power spectral density function for Z. Generally, we rather than obtaining the power spectral density function matrix of a single Z, or that is for a particular value of mode, we wish to find out the entire Z matrix, that is SZZ, that is the power spectral density function matrix of all the Z's, and say that matrix size will be equal to m by m, where m is the number of modes that is considered. So, in that case, we can write down this basic relationship, that is Z vector will be equal to a H matrix, small h matrix, which will be a diagonal matrix, because all the values of Z, they are uncoupled. So, therefore, this H matrix will be a diagonal matrix. P is a modal load vector having the size of the same number of modes m, and once we have that, then we can write down SZZ to be equal to H into SPP into H star T. And since this is known, these and these quantities are known, only one has to find out what is the SPP matrix. Now, SPP matrix, any term of the SPP matrix can be obtained from this relationship, that is SPI Pj, that is equal to JIT MR x double dot G into RT MT and JI, or sorry JJ, that is between I and J, the cross power spectral density function of force, that is the modal force P and modal force Pj, the cross power spectral density function between them. So, that can be given by this equation, and only thing is that you to note is that this is the I and this is the J. So, one should only take note of this I and J over here, that is this will be the ith mode shape and this will be the jth mode shape, and rest of M and R etc., they are known. So, one can obtain the value of SPI Pj. Mind you, Sx double dot G here is again a matrix of the power spectral density function of ground acceleration, and which requires again the requires a determination of the cross power spectral density function terms, which comes from the coherence function. So, once we get SPI Pj terms, or every term of the SP matrix, then SZZ is known, and once SZZ is known, then we can go back to our modal equation, that is x is equal to phi into z, or mode superposition equation, and if this holds good, then Sxx will be equal to phi into SZZ phi t, and say if we take only the m number of modes, SZZ will be m by m, and they will be n by m and m by n respectively, and we will get a power spectral density function of the displacements in the structural coordinate, and we will get this matrix size will be n by n. So, we can see that in the case of the modal spectral analysis, what we do is that we have the same formulation that we have done for the mode superposition technique for solving the problem in the frequency domain and time domain, and extend it to obtain the power spectral density function of the generalized coordinate by using small h, that is the frequency response function of a single degree of freedom system, and we can obtain turn by turn, that is we can obtain the Sz for each mode, or one can obtain the power spectral density function matrix of Szz, and that would be given by this. Mind you, this Szz is not a diagonal matrix, it will have cross terms. So, these cross terms denote the correlation between the power spectral density functions of Z1 and Zi and Zj. So, I stop at this today, and we will solve a problem, that is the problem that we solved for a cable state bridge, and that will take an example to illustrate the use of the modal spectral analysis.